Any complex system has to have within itself a communication system in order to coordinate all its activities. I'd like to start by showing you a short film that I think illustrates the principle.
Steer 174.
Steer 174.
Gyro check, sir. Gyro is correct.
Good, thank you. Are we quite happy?
Yes, sir.
Both inners slow ahead.
Both inners at the slow
Stand by.
ahead.
We start using the turn, sir.
Midships.
Yes.
Port take 20 south. Stand by 10 seconds.
Starboard 169. Yes, sir.
Port inner stop.
Port inner repeated. Stop, sir.
Port inner confirmed stop, sir.
A ship has a single job to do and must act as an entity. But the Ark Royal had a crew of 2,200 and countless machines that were automatic or manually controlled. And there was a hierarchy of responsibility going up to the bridge and ultimately to the captain. The whole was tightly coordinated by hundreds of miles of communication wiring throughout the whole ship. It's exactly the same within our own bodies. Our bodies contain about 1 million cells, each specialized to do a specific job, but we are much more than simply a colony of cells. We are an individual human person, and we have a similar wiring system within our bodies. This is a representation of mind. Somebody called that the bionic pie. If I just hang it on the wall. The bridge, of course, is the brain. The brain consists of a large number of different centers, each acting as a special purpose computer with its own job to do in a hierarchy of such systems. Coming down from the brain, there is the spinal cord running down through the backbone, with subsidiary computers controlling events at a more peripheral level. And all the way from the brain and the spinal cord, there are large numbers of nerves that run out to every single organ in the body, and they consist of trunks of nerve fibers, individual communication channels, and the nerves branch and branch and branch, so that each branch contains fewer and fewer until the finest tips, which cannot be seen on that diagram, contain just a few nerve fibers terminating on some specific organ, which either is controlled by the nervous system, by motor fibers, or is a sensory organ sending information to the brain by sensory fibers. Let's put all this into action. Computing a ballistic trajectory is quite a complicated thing to do. It starts as a parabola, and in a vacuum it would be. But in air resistance slows the thing down, and the actual motion of a missile is quite complicated. Let's compute a few with our own systems. Catch. Try again. One more. Still, the point is there, I think. You all know how to catch a ball. The information is received by your eye, which works out how the thing is moving, where it's going to be. The brain sends out the information to your muscles, makes you move into the correct position. Some of you stood up, move to one side or another, you put out your hands at the right time, and you close on the object, and you can all catch a ball, although mathematically it's an extremely complicated action. The messages, I said, are carried in nerve fibers. So let's look at an electron microscope picture of the cut end of a nerve fiber, a nerve with a few fibers. Those tubes each contain one nerve fiber. The total effect is rather like a telephone cable, such as you see in holes under the pavement, where the engineers have to connect them up to make sure the right connections go to the right subscribers in offices or homes. There are similarities. One of the biggest differences, however, is that with cables you have to have two wires, one to carry the current out and the other to bring it back to complete the circuit, so they work in pairs. In the nerve, each nerve fiber carries the message all on its own, and it works in rather a different way. The problem is that our bodies are made of water, and water doesn't conduct electricity very well. It only conducts at all if it contains dissolved ions. And even then, the conductivity is about 50 times worse than that of copper, which is used for making cables. To start to illustrate this, I'd like to carry out a small experiment, and I need a volunteer. Would you like to come down, little girl in blue? If you come around here, please. Come and help me with this experiment here. Here we have a conductivity bath. It's a bath of very pure water with metal plates either side, and there's a battery connected through the water and through the meter, and as you can see from the needle, it's not passing any current at the moment. Now, if you put a metal bar across there, it will conduct current. If you'd like to put that across, you'll see the needle go over. There we are. Take it off, and back again. Right. So the metal bar conducts electricity, but the water doesn't. Now, I've got a solution here, which I assure you is quite clean, and it's quite safe to have just a little taste of that, and tell me what you think it tastes of. Sugar, that's right. In fact, we've got it labelled on here, sugar, which everybody can see. I would like you now to pour that into the bath and see what happens to the needle. Pour it straight in. Just a very little current, not very much. We can say that sugar does not conduct electricity. Now try a drop of this solution, just a little drop on your tongue I think will be enough. And tell me what you think that tastes of.
Salt.
Salt, isn't it? It's very strong. You might like a drink of clean water now. Well, now pour the salt solution into the tank. And it conducts very well indeed. Salt does conduct. Fine, thank you very much. Salt conducts because the molecule, sodium chloride, when it dissolves in water, splits into two halves, the sodium and the chloride halves, and they don't share the electrical charge equally. The sodium, Na, goes positive. The chloride takes negative, equal and opposite charges, and those charges can move when there is a voltage applied and make the water conduct. Sugar does not split up in that way and does not conduct electricity. If we look at a piece of a nerve fiber, we see that the cell produces large negatively charged ions called A-, meaning large anions, which are trapped inside the cell and can't get out. It also actively excludes sodium ions, the Na+. And that leads the inside of the cell to be strongly negative. To some extent, this is compensated by passive migration of chloride ions, negative, out, Cl, and potassium ions, K+, inwards, which are then not in equal concentrations inside and out. When part of the cell fibre becomes active, however, what happens is that there is a leakage of sodium. Sodium is allowed to leak into the cell, thus carrying positive charge inside and making the inside go positive. As soon as that happens, about a thousandth of a second later, the cell becomes leaky to potassium, and potassium moves out, taking positive charge outside the cell again and restoring the status quo. If we have an active region in the middle, which becomes positive, then electric currents are set up from the active region to the surrounding regions. The currents go from positive to negative, and they cause the resting region to become leaky to sodium, so that region in turn becomes active, and the action potential moves down the membrane. And it can move at quite a high speed. At the end of the fibre, there is a slightly swollen terminal which contains a number of little capsules called vesicles, and inside those are chemicals that are made by the cell. The action potential comes along to the end there, and it causes a few of those vesicles to come to the outside of the cell, burst and release their contents, and they diffuse across to the next cell, which is just a short distance away across the gap. In some nerve terminals, those chemicals cause a leakage of sodium, so that they tend to excite activity in the following cell. In other terminals, different chemicals cause the leakage of potassium, which makes the next cell become less active. Now, in the brain, that next cell may have 10,000 terminals coming onto it, some exciting it, some inhibiting it. And, well, its own action is determined by the sum total of all that happens, all these 10,000 inputs. So it's rather like a computer that is receiving a whole lot of information through different channels and having its own activity coordinated. When it fires its own action potential, that may go out through branches of the fibre to as many as several thousand other cells. And this is a real piece of tissue. It shows a motor fibre branching to terminate on muscle fibres, and each receives a terminal from the motor fibre, and that whole collection forms a motor unit. When we make a muscle contract, an action potential goes down, and each one makes a number of muscle fibres contract, and the whole muscle is controlled in that sort of a way. Well, I'd like to show you now an actual action potential. We're going to show it in earthworms. Earthworms have, in common with other invertebrate animals, their nervous systems just inside the skin on the ventral or underneath side. Here are some worms living in a wormarium. There's one on top here. And you know that if you poke a worm, it will contract quickly along its length. Let's see if this one will do it now. Pulled in its tail quickly. This is part of an escape reaction. If a worm is unwise enough to put its head out of its burrow on the lawn during the day, and a bird comes along and pecks at it, it'll pull back into its burrow very, very quickly. It's important to do it quickly. But a worm can't afford to run its nervous system at high speed, because the speed at which an action potential goes depends, for electrical reasons, on the size of the fibre. Big fibres conduct faster than small ones. So for its escape reaction, the earthworm has a couple of giant fibres that run along the body and tell it to contract to get back into its burrow as quickly as possible. We have a demonstration here. I'm going to be helped by David, a graduate student from Queen Mary College. Hi, David. What we've done here is to hang an earthworm over some wire electrodes from which we can record the action potential of its giant fibre system and stimulate action potentials by passing a small shock through the body of the worm at the other pair of electrodes. It would, of course, be terrible for this experiment if the earthworm were to wriggle, so this one has been sedated by being dropped for a few minutes into 10% alcohol, roughly equivalent to the strength of table wine. This doesn't seem to do them any harm at all. They recover afterwards and they don't even seem to get a hangover. So I will now give it a switch on the stimulator. And what we see here on the screen is a spike representing the initial shock that goes down the length of the worm at the speed of light. If I go to the next scale, I can turn it up a lot more and I get a slower potential there from a second, smaller and therefore slower fibre system. Let's just measure the time interval. Can we record that, please, David, on the screen? The speed of this now then is about 9 milliseconds, and the distance travelled is near enough 9 centimetres. So the speed then of the action potential in that faster giant fibre is just about 10 metres per second. Well, I said that this giant fibre is used for escape reactions. One of the most spectacular of giant fibre systems is that contained in marine fan worms. It's a different group of worms that live on the bottom of the sea, on a muddy environment, and construct for themselves tubes of mud in which they live, and you see some here in the tank. They push their front ends out of the tube as a big fan that collects food by filtering the seawater and collecting microorganisms. But of course that's a very tempting morsel for any fish that's going by, and they're very vulnerable. The only escape they can make is to whip back into their tubes at high speed. Now, I'm not going too close to the tank because as I walk up, they often react just to my footfalls on the floor. I creep up on them now. See these very beautiful crowns of tentacles here, but if I tap the tank, they all shoot in. They nearly all shoot in. And that is brought about by a single giant fibre that runs down the body of the worm and is truly enormous. Fan worms have some of the largest fibres known. A section through a fan worm, at the bottom there, just above the skin, is the nervous system containing lots of small nerve cells, and above that, the pale area arrowed there is the single giant fibre, which is much bigger than the whole of the nerve cord, of the rest of the nerve cord. It's up to 1.8 millimetres in diameter, which is huge. It was so big that for a long time people thought that this was a strengthening skeletal element and didn't recognise it as a single nerve fibre. Nevertheless, that fibre can only conduct at 15 to 20 metres per second. Now, vertebrate animals, starting with the fishes and coming up to ourselves, have a way of miniaturizing all this by a clever trick that allows them to get very much higher speeds without going for giant size. I should have pointed out at the time that those are not actual nerve fibres that we're seeing there, but the wrappings of fatty cells that wrap around them at intervals and insulate them so that long sections of the fibre are not able to be active. The fibre itself has a membrane that's so thin you wouldn't see it in a picture of that sort. There is the nerve, a short section of the nerve fibre again, with wrappings leaving naked patches at intervals. Now that is not to scale. The diameter of the system might be between 1 and 20 thousandths of a millimetre. The distance between the naked regions will be about 1 millimetre. So the currents that are formed from an active region have to flow all the way around that fatty sheath 1 millimetre ahead, and it acts very much like a repeater station along an undersea cable, telephone cable. Well, if the action potential can only be of one size. It can only go from 70 millivolts inside negative to 50 positive. Messages transmitted down a fibre can only be sent by coding the sequence of the action potentials themselves. And this is called pulse rate modulation. A sense organ receiving a strong stimulus sends a very rapid train of impulses down the fibre. A weaker stimulation will send a slower rate. But in any one fibre, they're all the same size. We're going to show this on a sensory preparation from the leg of a cockroach. I expect you've all seen cockroaches. Nobody likes cockroaches, but we're all, I'm afraid, familiar with them. They come into many buildings and extremely difficult to get rid of and are regarded as a pest, though honestly they don't really seem to do very much harm. Like all insects, they have 6 legs. The 6 legs are jointed and have spines on them. The spines are sense organs that are sensitive to touch. When the leg touches something, the spine is bent, and messages go up a nerve fibre to tell the nervous system. Similarly, every joint has its own sense organ, so that the position of the joint and the stresses and strains are measured, fed back to the nervous system, and are used by it to control the movement of the leg, to synchronize walking. You imagine that walking with 6 legs needs much more synchronization than walking on 2 legs, and also to control its posture. So Chris, from another graduate student from Queen Mary College, has set up a preparation here in which we have the leg of a freshly killed cockroach, and he has hooked up an amplifier to the nerve in that leg and pinned it so that I can pull on a string to the distal part of the leg and alter the angle of the joint, and I'll be doing that to the leg of a cockroach. When I move it a small amount, we should get a small burst of impulses. The more I move it and the more quickly I move it, the longer and the stronger the burst. But the impulses won't change. We shall see big impulses and small impulses on the oscilloscope and hear them as clicks. But the big ones and the small ones are from different fibres that may be nearer to or close or further from the recording electrodes. All right. I take the string here, and when I move the leg, move it, move it, move it. Now give it a bigger movement. Little movements give small numbers of impulses. Big movements give a more rapid train. Thank you very much, Chris. Another thing you probably noticed was, after I'd moved it, the impulses came rapidly and then died away quickly. Although the nervous system is using a pulse rate modulation as its code, the rate at which they fade away is also a part of the code. Exactly the same pulse rate modulation code is used for controlling muscles. And we have here some locusts. We've chosen locusts because they've got extremely strong leg muscles. If you've all heard of locusts, perhaps they're not quite as familiar as cockroaches because they don't live wild in this country. They're just large grasshoppers. In tropical regions, they sometimes build up to tremendous numbers and then start migrating as a flock, eating everything in their path, and they become a great nuisance as a plague of locusts. But in small numbers, the non-migratory phase, they're really quite attractive looking animals. I'll just pick one that looks a likely collaborator. And you see these enormous back legs now with which it jumps. Like all grasshoppers, they're very good at jumping. Let's put him there and see if we can make him jump. An insect that size can jump 2 or 3 meters, which is a long, long jump for such a sized animal. Come along. He jumps down there. Come on, man. Hardly a good performer, is he? There we go. Pretty long jump. It was worth waiting for, I think. Let's see if we can see that in slow motion. Of course, he's gone so fast that without a really high-speed camera, it just becomes a blur. Well, we have a preparation here, again, that has been prepared by Chris from Queen Mary College, in which he's taken a freshly killed locust and tied its leg so that we can stimulate the motor nerve and make the leg, the jumping leg, move. And here, you see, it's connected up to a transducer that measures the movement, so that every time we give it a stimulus, the movement is recorded on a paper trace down here. Right, can we just give it slow twitches? That's right. Fine. Here we're giving one shock every so often to the leg nerve. I think that's fine, thanks, Chris. And each time the muscle contracts. Now, unlike our own muscles, all the muscle fibers in that muscle are controlled by a single nerve fiber. So there is only one size of twitch that can be produced by a single action potential. However, the contraction is fairly long compared with the duration of the action potential. So we can fire a burst of action potentials so that their effects all add together and produce a bigger contraction. Could we accelerate the rate now then, Chris? There it is, going faster and faster. The faster it goes, the more it contracts until you get a big, powerful deflection there. Okay, thank you. Let it relax. Now can we fire a very short but very rapid burst on a faster motor speed, and that's the sort of contraction that would catapult the locust into the air. It can afford to contract at its leisure afterwards. So the message down that nerve fiber has to be controlled by the brain to make the muscle do what it wants. When the action potential reaches the end, it goes across a gap by chemical transmitter substances again, as in the brain, and causes an action potential to flow over the muscle fibers. There'd be no point in a muscle fiber contracting at one end and then later at another end. One bit would simply stretch the rest. It's all got to contract at once. So again, an action potential runs rapidly over the muscle fiber. It all contracts as a unit. All our muscles, therefore, produce electrical activity. In the electric fish, that has been exploited, not for its contraction, but by cells that have lost the ability to contract, but exploit instead the electrical properties. Each cell can produce about 75 millivolts, and that may not seem very much. Remember in lecture, an earlier lecture in the series, we saw some fishes communicating by producing shocks of about 2 volts. Some fishes can produce very much more. 75 millivolts, if you have a stack of 2,000 cells, which is not a lot for the body, then if they're all fired at once, can produce 150 volts. And that's about the voltage that we would get from this electric catfish. Electric catfish live in rivers in West Africa. I once saw somebody coming back from a fishing expedition with one that long in the bottom of his dugout canoe. And I thought, I was rather glad I hadn't gone fishing with him, because if this can produce 150 volts, 2 or 3 times the size would be very much stronger. Well, the electrical activity from our own muscles can be put to use clinically. We have here an apparatus that has been developed for clinical use. It consists of an amplifier and stimulator in combination in one box, so that a doctor and technician can use them to record electrical activity within the body. This equipment has been developed for a very wide range of tests. And if you make equipment become very flexible, then you end up with rather a lot of controls. So this particular set is controlled instead by a microprocessor. Now, the first volunteer is Tibor. We plug him into the amplifier. And what we've done here is to put 2 electrodes on Tibor's hand in this fleshy part of the palm here over the muscles that make his fingers contract. You can hear the activity, see it on the screen. Tibor has agreed to give himself shocks to the nerve that controls those muscles in the side of his wrist here. Okay, are you ready, Tibor? See how his fingers are made to contract each time with a pulse? Before, all the different muscle groups were firing slightly out of phase. Now we're making them all fire at once, and we get a smooth curve, which is the action potential from all the muscle fibers synchronized together. We'll now do a slightly different experiment where Tibor will stimulate the same nerve up at his elbow. Exactly the same action. It's the same nerve, but at a different point. That looks fine. The first action took 4.58 milliseconds. The second one comes at 8.54 milliseconds. So the time difference that it took for the action potentials to go down Tibor's arm from there to there is 3.96 milliseconds. That's thousandths of a second. Now I just measure the distance. Where did you have it, Tibor? Just on there, right? I'll measure this down to there. You'll make that 30, 29.
29.
29, yes. 29 centimeters. And the answer is given by the computer as 73.2 meters per second. That is an appreciable proportion of the speed of sound. What would it be? It's more than 1/5 of the speed of sound. Fine, thank you very much, Tibor. If our optic nerve fibre from the eye, which contains 1 million fibres, had to run on the giant fibre principle of the fanworm, then it would have to be over 1 metre in diameter from each eye, which would be quite ridiculous, and it would still conduct very much slower, about 1/5 of the speed of the fibres we've just seen in Tibor's arm. You can imagine how we would have to redesign sports. If we could only see at 1/5 of the speed that we do now, I think table tennis, for instance, would be quite impossible. And we'd have to invent a whole lot of new different sports. Well, those were motor impulses that we were measuring the speed of there. We can also do it with this equipment on sensory potentials. And Nick here has come as a volunteer, hello Nick, to show us how we can record sensory potentials going from the skin to the brain. He's got a slightly different arrangement where he has 2 ring electrodes around his middle finger, and the electric shock will be applied to his finger, and of course he will feel it. Nevertheless, there is a way of recording those from surface electrodes placed on the surface of the skin, just above the position of the nerve, and the computer registers the response each time that we give it a shock. Right, would you like to run, please, Ray? The bottom line is the trace each time. The top line is the much clearer response added up by the computer. And again, we can measure the timing of that. It took about 3.1 milliseconds for that shock to get across Nick's palm to the position where we're recording it on his wrist. Thank you very much, Nick. So now we're actually going to measure a reflex, and Nicholas has come down to act as a subject here. And I'm going to test a reflex you've probably all had done on you. It's one of the commoner ones that is done by doctors to test your reactions. What he does is to make you relax, and then he taps you just below the knee with a little hammer, doesn't he? This muscle on the thigh works the knee joint by having a tendon that goes over the joint to the shin bone. Now, we have a very ingenious little hammer here. It's just like the ones that doctors use, with the addition that it has a switch at this point here, this little ring, and on impact it gives an impulse that tells the computer that precise moment when the impact occurred. So the computer can then look for muscle activity, but the message will go first up to Nick's spinal cord, and then new orders will be sent out to the muscle, and by this little pair of electrodes strapped to the muscle of the thigh, we'll measure the response. So if you can cross your legs, please, Nick. Absolutely relaxed, okay? Just let it dangle. You don't have to do anything. Shut your eyes. Just let it relax. Just hang free. There we are. That's quite a nice response. Now, we can measure the time of that response, again, with the computer screen. "29 milliseconds. 29 thousandths of a second for the stretch to be measured, processed, the message to go to the spinal cord, be processed, send orders out and make the muscle contract. But now we're going to do it a different way, not by a reflex, but by a voluntary action, a reaction time. Can I have the bell, please, Ray? I'm going to send the message in through Nicholas' ears. I'm going to use the same hammer, but to tap a bell. And what I'm going to ask him to do is to kick his leg when he hears the sound, to kick it voluntarily. Then the message goes in at his ear, is thought about by the brain, processed, sent down the spinal cord, and out to make the muscle contract. All right, are you ready, Nicholas? Nice big kick, but it's a lot slower than the reflex. Of course, it would be. Let's try again. One more time. You're remarkably consistent, Nicholas. It comes in exactly the same place each time, but much slower than the reflex. Let's just look at that time now. The first activity there is round about there, which is 144 milliseconds, as opposed to 28 the first time. So reflexes really do work. They get on with the job in hand and just consult the brain later to see what finer controls may be necessary. Fine, thank you very much, Nicholas. You can have fun with reaction time yourself. You don't have to have equipment of this caliber. I would like to choose a couple of volunteers for this one. Would you like to come down, please? And you in red, please. We're going to play a little game now. I'd like you to sit in the chair, rest your arm on here with your hand sticking out. Hold your fingers out like this, because I have here a special piece of property called a £5 note. You know what these are? Now you hold your fingers like that, And I'm going to drop it, and all you have to do is catch it, right? You ready? All right, all right. Don't go away, don't go away. And your name is?
Gregory. Gregory.
Gregory, fine. Would you like to have a go, Gregory? Rest your hand on the end of the arm. All right, don't go away, stay there. It is, in fact, extremely difficult to do if you could do it at all. But you can measure your reaction time using apparatus no more complicated than a single ruler. And I'm going to set up a competition now between these two young men to see which of them has the faster reaction time using a ruler to measure it. So, if I hold the ruler between your finger and thumb with the 0 centimetres exactly in position, then when I drop it, you've got to catch it. All right, that came out at about 270. Okay, now we can see how long that is. You all know that there's a simple formula for the relationship between distance, time, and acceleration. If you want to work out that time in terms of centimetres, you simply divide it, we said 270 millimetres, so that's 27 centimetres. Divide it by 490 and take the square root. 234 milliseconds. That's still under a quarter of a second. That's not bad. Now, Gregory, would you like to stand here and let's see how well you can do? Even better. 221. Let's just work that out. 221 divide by 490 and take the square root is 207 milliseconds. So it's very good. So I think you get to keep the ruler.
Thank you.
Now, just a minute, one more thing. If you'd like to get your calculators out at home, you could take a ruler or another bit of stick and calibrate it directly in terms of time, how far it will drop in a given time. Remembering, of course, the marks get further and further away as it accelerates. So we have this stick that is calibrated directly in time. I thought you might like to try me, each in turn, and see what my time is if I sit down here now. You're going to try me first? That's the 0 position down there, you see. What would you reckon that is? 230? 230 or so, maybe a little more. It hasn't got very fine divisions, but of course you can make it as fine as you like. Right? Just about the same again. I'm a little bit slower than you are.
Yes.
Thank you both very much. Our brains contain about 10,000 million cells connected up in very complicated ways, as I indicated earlier. And most of the processing goes on by electrical nerve impulses that are passing to and fro in this three-dimensional structure the whole time. You might think, therefore, that to actually demonstrate an action of the brain from outside the head would be an extremely difficult thing to do. However, again, computers come to our rescue. Our next volunteer is Catherine. What we've done is to put electrodes on Catherine's head, just parting the hair slightly, and we'll be looking at the electrical activity of her brain inside the head. But of course, an awful lot is going on in there. Her brain is receiving messages about all sorts of things all the time, sensory messages from all parts of the body. She's probably not paying attention to most of them, but they're there, and she can pay attention to them if she wants to. Nevertheless, the computer can sort out some responses. And we're going to look at what happens in Catherine's brain when she sees something happen. The visual stimulus is this checkerboard pattern, which twice per second will change the position of the blacks and the whites. They'll interchange. And that turns out to be a very strong signal. Each time that it happens, there will be a very small proportion of the activity of her brain will be devoted to seeing it. We shan't see that response. We've got the loudspeaker on, have we? Now, would you clench your teeth for a moment? Right, okay, relax. One more time, and relax. Let your jaw sag a little, mouth slightly open if you like, and now we'll start to stimulate you by changing the pattern. On the computer screen, the lower trace again is giving what happens each single time. The upper trace is giving the computer sum of all those responses. Now, I can't see a response in that bottom trace any one time. If I think it's there one time, then it's somewhere else the next time. But the computer is seeing a regular pattern within what is apparently a random process. In fact, the sum is getting so big at the moment, it's limiting, giving a square top. But we can adjust that afterwards. Oh, there it goes now. There we are. I think we've finished the run, haven't we? We now see a downward excursion of the top trace, just as we would expect it. And it occurs 103 milliseconds. It's about 103 milliseconds after the picture changed from black to white to provide a stimulus. Thank you very much, Catherine. I think it's quite remarkable to be able to stick wires on the outside of somebody's head and to detect a response from this incredibly complicated brain structure that's lying inside. Well, the brain looks like this. This isn't a real one, it's a plastic one, but it's about the right size, so you can imagine it somewhere in here. The part of the brain that responds to visual signals and sorts out what you are actually seeing is this bit on the back here. But probably with that time relation, what we were seeing is an intermediate switching point in what's called the midbrain. If we take this model apart into two halves, we were getting it from this region here, which is where the signals first come in and are later sent for higher analysis at the back. It's this point here that is responsible for visual reflexes, such as the blink reflex, where things happen quicker than you have time to think about them, and you don't need to analyze the picture in great detail. But the brain doesn't control the body entirely by sending out action potentials through nerve fibers. It has another means. For steady maintenance activities within the body that don't require high speed, but do require a very sensitive and subtle control over the whole of your life, it has means of control by chemicals called hormones. The chemicals are secreted by this little object here, little lobe called the pituitary gland, which is underneath the floor of the brain, and as you see is on a little stalk, and is painted a sort of browny pink colour here. That releases hormones in a very complex way, 8 or 9 of them. 2 of them are released directly by nerves that go down the stalk and release hormones into the bloodstream to circulate around the body, where in turn they affect organs that are sensitive to those particular chemicals. Others are released by chemicals that are produced inside the brain itself, in the floor of the brain, are carried the short distance in the bloodstream to the pituitary. There they cause release of other chemicals which go around the body to the so-called target organs, and some of those target organs may in turn be hormonal glands. So it can be extremely complicated. To give an example, if the blood temperature starts to drop, then the blood reaching this region of the brain called the hypothalamus gets just a little bit cooler. Very sensitive temperature detectors cause the release of chemicals that release another chemical from the pituitary that circulate round to the thyroid gland in the throat that releases thyroxine, which increases metabolism, so you burn more food and get a little bit warmer. And all the time, the hypothalamus is monitoring the effects that it's having by the secretion of these chemicals. And this is feedback again. We've met a number of cases of feedback. The brain is always seeing what is happening in response to the instructions that it's issuing. And any self-regulating device has to have feedback in that sort of way. I'm going to finish with a couple of demonstrations of feedback. The first one is the iris. You know that if you walk into a bright light, the iris in your eye closes down, makes a smaller hole in the pupil, and cuts down the amount of light. In the dark, it opens up again. That is a form of reflex. Let me put the chair round here, about there. And now this time I'd like somebody with really nice blue eyes to... You've got nice eyes. Would you like to come? And your name is? Claire. Right. Would you like to sit here then, Claire? And I'm going to shine a little light into your eye to make your iris work. Okay? That's why I needed blue eyes, so that we can get a nice picture on the camera. All you have to do is to stare at the center of the lens there. Right. Everybody can see Claire's eye now. I've got a little torch here. I just rest my arm and flash it into your eye. It closes down and opens up again. Closes and opens. That's a normal reflex. If I shine the light so that it just comes in over the bottom of the iris, like the rising sun, then the eye will see the light, close the iris down, and cut the light off completely. So it won't see the light, so it'll open up again, and let the light in, so it'll close again, and it'll oscillate. And that's generally the response of self-controlling automatic systems when you upset them in that way. Just stare at the camera lens. You see it oscillating? I'm holding it as steady as I can. It's going with a period of about 2 or 3 seconds. Thank you very much. Doctors sometimes use that, again, as a test of function within the eye. The next demonstration is related to the fact that you can see clearly even when you're moving. If you're a photographer, you know that you have to hold the camera very, very steady. Otherwise, the picture comes out blurred. Even if you use a shutter speed of about a 50th of a second, you've got to hold the camera very still. Now, your eye is averaging equivalent to a shutter speed of about 25th of a second, which is quite a bit slower. So you might think that to see clearly, you have to hold your head very, very still before it becomes clear enough to see. And yet you can see clearly when you're walking or running or riding a bike or a horse. As your head moves, messages go out from the brain to the muscles in the eyeball to control the movement of the eyeball. And those messages originate in the ear. Here's a model of the ear. That's the bit you see on the outside. Here's the ear canal that goes in to the eardrum. And the sound goes across deeper into the head, into the inner ear, and is actually detected in this bit here. But attached to that are these 3 sets of canals here, which are very sensitive to head movement. Whenever your head moves, they tell the brain exactly what movement it is, so that the brain can then control the eyeball and keep the eye steady. That is another form of reflex loop. I'd like one more volunteer for this, please. Would you like to come out, little boy in blue? What's your name, please? Matthew. Well, Matthew, I'd like you to do two different things in turn. The first one is to hold this piece of paper straight out and nod your head up and down, as I'm doing now. Watch. Okay, are you watching what I do with my head? And as you nod your head up and down, read aloud to show us that you can still read it. No, turn this way, please. That's it.
Between the rolling prairies of the plains
Keep your
and
head
the
nodding.
thundering breakers of the Pacific lay an area measuring
Yeah,
more than a
that's
third.
okay. Thank you. That was easy, wasn't it? Makes no difficulty at all. Although your head is moving a lot, your eye can stay steady, and it is really moving within the eye socket. Now try keeping your head quite still, but move the paper up and down with your hands at the same speed and through the same angle, and again read aloud. Now, turn this way, please. Fine. That's it.
Between the rolling prairies of
Try again.
between the rolling prairies. Oh, am I allowed to move my eyes?
Oh yes, you're allowed to move your eyes, but try and keep your head still.
Between the rolling prairies of the plains, the thundering breakers of the Pacific lay an area measuring more than a third of the continent.
That's very good. Can you keep going at that rate? Just about, yes. It is difficult, isn't it? I think most people find it almost impossible. Although you're making the movements yourself, you see, it becomes very difficult to follow. Would you all like to try it? It's easy if you nod your head. It's more difficult if you move your arms. Are you convinced? Of course, if you read the paper when you arrived, wondering what this was on your seat, then of course you rather know what to expect. I suggest you take the paper home and try it on somebody else who hasn't seen what's coming and see how they cope. Thank you very much. It's easy in one case because the head movements are measured and control reflexes. There is no such link between the arms, although they're your arms. You might like to try moving it yourself and then getting somebody else to move it. It's just as difficult either way. Well, the brain is a large number of computers working out all these functions, controlling our bodies. In the next lecture, we'll be looking at real computers and how they can be hooked up to other effectors and mechanical sense organs to make robots. Thank you very much.